Let's do number 1 for electricity, chapter 22. Number 1 has 4 parts. I'll give you guys a few seconds to solve the question and then we'll check together. Let's do part A. State Gauss's law in words and give its mathematical expression. I won't say I won't write the words, I'll just say them and then I'll give the expression. So Gauss's law basically says the total electric flux of a closed surface is equal to the charge enclosed in that surface divided by epsilon 0, which is the permittivity of free space. So I'll just write the formula. This means phi E is the symbol for electric flux, is equal to Q enclosed. You can use a capital Q, doesn't make a difference, over epsilon 0. Part B. When excess charge is placed on a solid conductor, where does it reside? It resides on the surface. C. Write the 3 forms of the general definition of the electric flux. So other than this, the one that I've underlined, there are 3 other equivalent equations. So let's just write that. Phi E is equal to the integration of the electric field vector times the area vector, which is equal to the electric field times dA times cosine the angle between them, which equals the perpendicular electric field times the area, and D says, just memorize these 3 equations. You don't need to know the derivation, just memorize. So I'm just boxing this, so you just have to derive this. D says, give the expression of the magnitude of the electric field outside a charged conducting sphere. Since it's a charged conducting sphere, we can use Gauss's law, and then when we derive, we should get E equals, because we want the electric field, not the flux now, 1 over 4 pi epsilon 0 times Q over R squared. This should look familiar because we should know this equals K. So isn't this KQ over R squared? Both work fine. Usually K won't be given, so you will have to use this equation. So both are acceptable answers. Let's move to number 2 now. I'll give you guys another few seconds. It's again of many definitions, so you can solve and then we'll check together. Okay, let's check together. What Gaussian surface is used to find the electric field outside an infinitely long charged wire? If we remember, we had derived in class the formula for this infinite charged wire. We had to create a shape for it. What shape did we use? We used a coaxial cylinder, or as in the homework they had mentioned, cylinder coaxial to the wire, which had a radius, arbitrary radius, that means the radius that we choose, R, and height h. B. What is the magnitude of the field of an infinite sheet of charge? It was E equals sigma over 2 epsilon 0. C says field between oppositely charged parallel conducting plates. E equals sigma over epsilon 0. Now I'll just erase the top part so we can have some space. So let me just erase, because I want to solve it on the same page. Now D. The shaded conductor shown in the figure carries a total charge of Q equals plus 7 nanocoulombs. The charge within the cavity insulated from the conductor is Q equals minus 2 nanocoulombs. What is the charge on the inner surface of the conductor? Okay, let's do it together. Now, first we have to assume what is the scenario when there is no inner charge Q. Let's just assume this wasn't there in the beginning. We put it now. We put it later on. So let me just cancel this. So we get rid of this. Since this big Q, right, it's a shaded conductor, this carries 7 nanocoulombs. And inside there won't be anything, because if we remember, inside a conductor, all the charge resides on the surface of it. When you put a minus 2, initially this was 0, this inner part, if we put a -2, we're putting -2 nanocoulombs worth of electrons inside. Now, one thing to remember, can we move protons? No, only electrons can move. When you're putting electrons in the middle, so let me just remove this. Now we have put a -2q. When you put electrons, won't the electrons here that I'm going to highlight in red, in this area, won't they be repelled and they'll go on the outside? They will, right? So when electrons are moving, won't the protons be left behind? So any charge that we put in the middle will induce an opposite but equal magnitude charge. So basically you will have +2 nanocoulombs in the inner surface, the red surface, or the black as I'm covered it up now. Why? Because when I put -2 worth of electrons, the same number of electrons will be repelled, leaving +2 nanocoulombs worth of protons left here. So we'll have a positive charge. And that's numbers 1 and 2 done. Yes. Let's move on to number 3. We have 4 enclosed surfaces S1 through S4 together with charges Q1 till Q5 are sketched in the figure. We have the values for Q1 till Q5. A to D are telling us to find the electric flux through each of the surfaces. So I'll give you guys a few seconds. I have displayed the formula for the electric flux here as a hint, and we'll check in a few seconds. Okay, let's check. So first they're telling us to find the electric flux for S1. Let me represent it like this. That's the Q enclosed. So Q of S1, whatever exists in that, over epsilon 0. There are no numbers in this question. We keep them in symbols. Now let's take a closer look at S1. I'm highlighting it in red. What is there in S1? Only Q1, right? Yeah. So Q1 is -4Q, so it's just -4Q over epsilon 0. That's it. B. Phi S2, I'm not going to put the formula again, it's just the same thing, but this time I'm going to do it in green now. What is in S2? Well, it's Q1, Q2, Q3 and Q5. So now coming here, it's Q1 plus Q2 plus Q3 plus Q5 all over epsilon 0, which gives me, what's Q1, -4Q plus Q, Q3 is -2Q, Q5 is -Q, all of this over epsilon 0. When we simplify, we should get -6Q over epsilon 0. Coming to part C now, let's go back to the thing. It's going to be phi of S3 is equal to, now let's use, I don't know, blue for S3. What is there in S3? All of this. Q4, Q3, Q4 and Q5 are there. So Q3 plus Q4 plus Q5, all of that over epsilon 0, and when you simplify you should get again -6Q over epsilon 0, which shows us that the fluxes through S2 and S3 are equivalent. Now part D, this must be S4 obviously. Let's see the diagram, and I'm going to use purple. This is S4, only Q5. Okay, Q5 is -Q, so let's go here. It's very simple, -Q over epsilon 0. So all I have to do to find the answers for these type of question is find the total sum of the charges enclosed in the thing over epsilon 0. And if you have numbers, you substitute. Number 4, part A. A point charge Q, 7 microcoulombs, is located at the center of a cube of side L of 0.150 meters. 6 other point charges are in there, each having a charge Q equals -1.5 microcoulombs, are positioned symmetrically about Q in the cube. What is the electric flux through one face of the cube? And they've given us this permittivity of free space, which is nothing but epsilon 0. I've given a quick diagram. We have the cube with 6 faces, 1, 2, 3, 4, the front one is 5 and the bottom one is 6, and then I've drawn the red dots to symbolize Q. And you guys can solve the question. I'll give you a few seconds. Okay, let's solve. Now we should first of all before finding the electric flux through one face of the cube, we should find the electric flux in the whole cube, right? But to find the electric flux of cube, shouldn't we find the Q enclosed of the cube? Right? This is our question mark. Epsilon 0 is always a constant. Well, to find that, let's call this, big Q is already taken. Q enclosed. Isn't it 7 plus 6, because 6 faces, times minus 1.5, which gives us minus 2 microcoulombs? That is the Q enclosed. Now, to find the electric flux of the cube of one face, how many faces do we have in a cube? Isn't it 6? So shouldn't it be 1/6 the initial flux? Yes, right? Now since we have minus 2, so it's minus 2 times 10 to the minus 6. Always use the correct units, SI units. 8.85 times 10 to the power of minus 12, and we should get, let's see, minus 3.77 times 10 to the 4. Now what's the unit of flux? It's very long, Newton meter squared per coulomb. And you guys can check. I'll give you guys a few seconds. Okay, let's continue with the next one, part B now. Let's read part B. The total electric flux through a closed surface in the shape of a cylinder is this. What is the net charge in the cylinder? Very easy question. We have the flux, we have epsilon 0, we need to find Q. Well, this is very easy. Since the flux is Q over epsilon 0, cross multiply, shouldn't Q equal flux times epsilon 0, which is simplified to 4.80 times 10 to the 4 into, let's see, 8.85 times 10 to the minus 12, which is 4.25 times 10 to the minus 7 coulombs. One trick to be aware of here is they might ask you how many nanocoulombs this is. Well, for that, that's 4.25 times 10 to the 2 nanocoulombs. They might ask you that, so just to keep it in mind. Because as you all know, 1 coulomb is equal, or wait, no. Yeah, 1 coulomb is 10 to the 9 nanocoulombs, so then you can just simplify from that. Let's do number 5 as well. A thin conducting wire, square plate, 35 centimeters on a side, lies in the XY plane. A total charge of 1.96 times 10 to the minus 8 coulombs is placed on the plate. We have epsilon 0. A says find the charge density on the plate, and B says magnitude of the electric field just above the plate. One question that some of you may be having is, we only learned the formula for the infinite uniform plate, right? But since this is a plate only 35 centimeters to a side, this is not infinite. But when they say just above the plate, we are so close to the plate that when you consider the size, it seems infinite. That's the trick here. So now we'll do part A. I'll give you guys a few seconds. Okay, let's solve it together. The symbol for charge density is sigma. That's the total charge over the area. The total charge is 1.96 times 10 to the minus 8 over the area. 35 times 35, but in centimeters, which is going to be centimeters squared. To make it into meters squared, you have to multiply by minus 10 to the minus 4, which gives us 1.60 times 10 to the minus 7. Let me just fix that. Coulombs per meter squared. Part B, electric field. You should memorize the formula. It's sigma over 2 epsilon 0. So this over 2 epsilon 0, I'm not going to write the number. And you should get 9.04 times 10 to the power of 3 newtons per coulomb. Significant figure is very important. Since we have 3 both sides, we should always put 3. That's question 3 to 5 done. Let's move on to question 6. A conducting spherical shell of radius 13 centimeters, which I've drawn here, carries a net charge of 5.07 microcoulombs uniformly distributed on its surface. A says find the magnitude of the electric field outside the shell, just outside the shell. B says inside the shell. And C says very far away from the shell, what is the magnitude? I've given you some formulas here to give a hint, and you guys can solve for a few seconds before I check with you. Let's check together. First, they want it just outside the shell. As we all know, if it's a conducting any conducting substance, it will have all the net charge on its surface. So when they're asking just outside the shell, we have a charge, so we have an electric field. Now, since we know that phi equals E dot dA, the integration of all that, which equals Q over epsilon 0, since we know it's a net charge which is uniformly distributed, we know that the field will be constant because everywhere is the same thing. It's very uniformly distributed. Like this, like this, like this, like this, like this, right? So we can take the integration out. So E times, what's the area of a sphere? 4 pi r squared equals 5.07 times 10 to the minus 6 over 8.85 times 10 to the minus 12. We can substitute r, make sure it's in meters. We should get that E equals 2.70 times 10 to the power of 6 Newton per Coulomb. And I want you guys to note on one special property here, that we can also use the equation E equals kq over r squared. Even though this is a very old equation, this also works here because it's a conducting spherical shell. Part B now. What's the magnitude of the electric field inside the shell? Since we know all the net charge is on the outside of the shell, is there anything inside? No. Very easy. E is 0. C. What is the magnitude of the electric field at the point very, very far from the shell? Since we know this equation that I'm underlining here, what they're asking us is, when r tends to infinity, what does E equal? Oh wait, sorry. What does E equal? Well, if r is infinity, then r squared is infinity. Anything over infinity, isn't it 0? So E equals 0. So this is why this equation helps us for this part C. Let's move on to question 7 now. A conducting spherical shell again, having an inner radius of 5 centimeters, an outer of 6, carries a net charge of 9 microcoulombs. If a plus 4 microcoulomb point charge is placed at the center of the shell, determine the surface charge density, or sigma. Part A says inner surface, B says outer surface. So what I want you guys to remark on is, this is just a shell, and the solid part of the shell is only the part I'm highlighting in black. Anything inside is hollow. You can think of, it's basically like a ring, a big metal ring, right? So the inner radius is 5, the outer radius is 6, so the thickness is 1. Let me use red. 1 centimeter. So I'll give you guys a few seconds. You can solve. I've given you some hints. The outer surface is 9 microcoulombs, and we have just put a 4 microcoulomb charge inside, and then we'll check together. Let's check together now. Now for the first one, they're saying the inner surface. Since we know that this part is the outer surface, this is the inner surface. Since we have put a 4 microcoulomb charge inside, this induces a minus 4 on this part. Now I have explained before, I'll explain briefly again. Basically, I put a 4 microcoulomb charge. Electrons are attracted to this area, they're attracted to positive. So minus 4 microcoulomb charge will be induced here. So this is equal to Q over A, right? Charge over area, which is minus 4 times 10 to the minus 6. Now we are talking about a sphere, right? So it's 4 pi. Radius is 5 centimeters, so 0.05 squared, which should give us minus 1.27 times 10 to the minus 4 coulombs per meter squared. Part B now. Let's call this sigma 1. Now we are looking for sigma 2. Outer surface. Now let me just erase everything actually, so that it becomes simple. Let's just make, okay, that's big, like that, and let's just quickly make another one smaller. Never mind. Yeah, this is good enough. Perfect. I had a minus 4 here last time and I had a plus 4 here. Putting the minus 4 here, what do you think this causes? Well, it causes a plus 4 here on the top part of the inner part, right? The top part of the inner surface. And that plus 4 again causes a minus 4 on the bottom part of the outer surface. Seems complicated. If you think about it, it's not. Since we know that the net charge has to be 9 microcoulombs, well, the sum of this and x has to be 9. X minus 4 equals 9, x is 13. So we have a 13 microcoulomb charge on the outside, so that our net charge is 9. So again, using this, Q over A, 13 times 10 to the minus 6. Now again a sphere, so now the radius is 6 centimeters. And this time you get a positive answer, 2.87 times 10 to the power of minus 4 coulomb per meter squared. Okay, let's continue, and this is the answer. You can check for a few seconds and we're moving on to number 8. Let's move on. Number 8. We have two infinite non-conducting sheets of charge which are parallel to each other in the figure. Both sheets, let's do parts A to C because they all have the same given. Sigma 1 and sigma 2 are positive. So I've split the question into two parts, so it's easy. I'll give you guys one hint that, you know what, I won't give you hints. We'll solve it together. Okay, let's check the answers. Now, we should know that the formula for a single uniform plate of charge, which is infinite, is equal to sigma over 2 epsilon 0. That's one thing we should be knowing. So let's just do it. At point A, what is the electric field? Now, if you think about the field as like a force, let's think of it as a force for now. Sigma 1 is positive. When it's positive, the field points away. So at A, it will point away. Let's call this E1, E caused by 1. And for sigma 2, it's positive as well, so it will point away, left and right. So this is E2. So isn't E at A equal to E1 plus E2, which is sigma 1 over 2 epsilon 0 plus sigma 2 over 2 epsilon 0. And now since sigma 1 equals sigma 2, they're the same. So it's sigma, which I've replaced by 1 over 2 plus 1 over 2 is 1. So over epsilon 0, which gives us 6.00 times 10 to the power of 7 newtons per coulomb. They've asked us, we don't need to say, but let's just say it's left. Extra details, it helps. So that's part A. The electric field points to the left at point A. Let's move on to part B. Now it's the same given, part B. And now we're just looking at point B. Now since sigma 1 is positive, it points away, so to the right. So this is E1. And now since sigma 2 is positive, it points away, E2. Since these two are the same magnitudes, they cancel out, 0. C. Again at point C, both are positive, both point away. Now it's again the exact same calculation, so it's everything here, copy paste, equals 6.00 times 10 to the 7 Newton per coulomb. Only one change. What is that change? It's pointing to the right. These questions are very easy. You just have to, read the question very carefully. DEF, sigma 1 is positive and sigma 2 is negative, but they have the same magnitude. Let's look at part D. Now in part D, we know that we're looking at point A. Since sigma 1 is positive, it points away yet again. But Since sigma 2 is negative, when it is plate a point is negative, the electric field points towards it. So it's like this, it points towards it. Since they both cancel out, 0. E and F. I'm going to skip E now, let's move on to F. Same logic for point C. Since sigma 1 is positive, it will point away. Sigma 2 is negative, it points towards 0. They both cancel out. Let me just erase this. And now we'll solve part E. Now, since sigma 1 is positive, points away, and since it's negative, sigma 2, it points towards it, so like this. So using that same logic, E at point B is equal to sigma 1 over 2 epsilon 0 plus sigma 2 over 2 epsilon 0. One thing to be careful of, in the calculations, we don't consider positive negative, it's always positive, okay? We're looking at magnitudes here, not direction. We're just looking at magnitudes here. That's sigma over epsilon 0, giving us the exact same answer as before, 6.00 times 10 to the power of 7 newtons per coulomb. Which direction? Pointing to the right. Let's look at number 9 now. A non-uniform electric field is directed along the x-axis at all points in space. The magnitude of the field varies with x, but not with respect to y and z. Axis of cylindrical surface 1 meter long and 0.5 meters in diameter is aligned parallel to the x-axis. Two electric fields E1 and E2 at the ends of the cylindrical surface have these two magnitudes and are directed as shown in the diagram. Find the electric flux entering the cylindrical surface at the left end. B says leaving at the right end. C is the net electric flux, and D is net charge enclosed. So I'll give you guys a few seconds. I've given a hint here and we'll check in a few seconds. Okay, let's check. Now what are these dA lines I've drawn here, these vectors? Well, the dA is the vector that is, it's the area vector and it's perpendicular to the area itself. Since the area of the circle is here, it's perpendicular, pointing outwards. Same goes for this. As we all know, a cylinder is two circles and a rectangle, which is bent. And I have a dA pointing upwards. I will not need this dA because if there is no E perpendicular to it or close by, I have no use for this dA. Now, many of you will notice that E1 and dA have opposite directions. That should mean that flux is negative, right? But since they're asking entering at the left end, we do not need to care about the signs yet. So sigma flux, the flux, electric flux from the left is equal to E dot, E dot dA vector. Since we know that the magnitude is 5 times 10 to the 3 and the area is pi r squared. Now what's r? R is 0.25 since the diameter is 0.5. And we should get 982 Newton meter squared per coulomb. B now, same thing to the right. Exact same formula. Now this time the flux, the electric field is different, it's weaker. By the exact same radius, the cylinder is not getting smaller and we should get 295 Newton meter squared per coulomb. So for parts A and B, we haven't really cared about the signs. For C, we will need to care. We want the net electric flux. Since I'll just erase this to help us. Since they have defined x, y, and z like this, and x is shown to the right, they are assuming the right side to be positive. Since my flux is positive, is to the right here, it's positive. But this flux is here because one is negative. So E net is equal to the flux to the right minus the flux that we got to the left, which is 295 minus 982, which is minus 687 Newton meter squared per coulomb, and that's the net flux. Last part D, they want the net charge. Very simple. This E, I'm just going to consider the net, is Q enclosed over epsilon 0, which means Q or Q enclosed is the flux times epsilon 0, which is minus 687 times 8.85 times 10 to the minus 12, and finally we get minus 6.08 times 10 to the minus 9 coulombs, and that's the net charge enclosed in the cylinder. Last question for chapter 22 is number 10. We have three hollow concentric spherical conductors. They are charged as follows. The inner one has minus 2q, middle one has plus 3q, outer sphere carries minus q. I'll give you guys a few seconds and you can solve. Okay, we should remember that the charge of any conducting sphere is usually at the outside. On the surface, so we have minus 2q here. I made the thing small so it's visible. Since we have minus 2q here, we cause a plus 2q to come here. I have explained this before. Now since the whole middle sphere contains plus 3q, this should have plus q. And this answers our first part of the question, which is asking what is the charge on the outer surface of the middle sphere. It is plus q. The sum has to be equal to the given. Now I'll erase that and we'll continue on. Let's make it small again and red. We have plus q on the outside. That causes a minus q here on the inner surface of the outer sphere. And since the whole outer sphere has to contain a minus q, outside is 0. So now going back, B says find the charge on the outer surface of the outer sphere. 0, because the inner surface has all the charge. And that's it. Very simple. Okay guys, lesson question number 1 of chapter 23. You guys can do parts A to C and then we'll check them together. Okay, let's solve part A. What is the electric potential energy of 2-point charges Q and Q0 at a distance r apart? It's just the formula. U is the electric potential energy, and since we have 2-point charges Q and Q0, it's K Q Q0 over R. That's it. B, a pair of charged metal plates. So let's draw it like this. Top is negative and bottom is positive. So we should know that the electric field is like this. And we have a positive charge Q. Since Q is positive, the electric field is anyways equal to EQ or QE, and it has to follow the same direction, so it's upwards. So far no calculations, all theoretical. Now part C is where we have calculations. The potential at a certain distance from a point charge is 720 volts and the electric field is 180 newtons per coulomb. What is the charge? So what we know is V is equal to 720 volts, E is equal to 180 newtons per coulomb. I would like to quickly go over the formulas for this. So V is equal to KQ over R, and we should remember that E is equal to KQ over R squared. Do we notice a similarity? We should notice that E can be written as KQ over R times 1 over R, right? Well, doesn't this lead to, let me just continue on the next page. Since we have that KQ over R times 1 over R, this is equal to V. So don't we get E equals VR? So isn't, oh wait, no, sorry. Isn't it E equals V over R? So when we cross multiply, we should get ER equals V, which means R equals V over E, which means it's 720 over 180, which is 4 meters, because radius has to be distance has to be in meters, like this. Now we're looking for the charge. We can use any formula. I personally prefer the V because it's less work. KQ over R, since it's 4, so 720 times 4 equals 9 times 10 to the 9, Q. If we simplify, we should get Q equals 3.2 times 10 to the power of minus 7 coulombs. Let's do number 2 now. We have again 3 parts in number 2. I'll give you guys a few seconds and we'll solve them together. Okay, let's check it together. Part A is asking us, the potential difference between two oppositely charged parallel metal plates is 120 volts and the distance between them is 3 centimeters. Find the magnitude of the electric field between the plates. We should know that basically the formula to find if the field is uniform, V equals ED. That is the main formula we should know. V equals ED, where D is the distance between the parallel metal plates, because the only time we have a uniform electric field is two parallel plates, right? So we're looking for the electric field, so that's E equals V over D. So 120 over 0.03 meters, because we want it in meters, that's 4,000. Now we have many possible units, but a good unit would be, since this is volts and this is meters, volts per meter. Part B now. The potential difference between two oppositely charged parallel metal plates is 450 volts. Find the work done on a charge of 40 millicoulombs as it moves from the higher potential plate to the lower. Now, since naturally, let's say this is the positive, this is the negative. The positive is at the higher potential. The electric field is naturally going from up to down. So there's no external work being done, so the work is conserved. So in this case, the work done by the electric field is equal to the charge VA minus VB, where VA is the high potential and this is the lower potential, which means 40 times 10 to the minus 3 into 450, which is equal to 18 joules. And now part C, when a charge of 20 microcoulombs is moved between two points M and N, in a uniform electric field, 240 microjoules of work is done. What is the potential difference between M and N? So now we have the work, we have the Q, but we don't have the delta V, right? Because VA minus VB is delta V. So it's very simple, delta V equals work over charge. Now we don't need to convert into 240 times 10 to the minus 6, because the micro cancels. So it's basically 240 over 20, 12 volts is the potential difference. Okay guys, let's move on to question 3 now. I'll give you guys a few seconds, you guys can solve it and then we'll check it together. Okay, let's check it together. Part A is asking, a positive charge of 4 microcoulombs is moved through an electric field to a point where the potential is 250 volts higher than before. Find the increase in potential energy of the system. Now, you can find some formulas relating potential energy to electric potential, but one you should know is W equals QV. We had used it last time, delta V, sorry. And what we should know is W is equal to delta U. This is also a formula. So if we substitute, we should get delta U equals Q delta V. And this is perfect. We want to find the increase in potential energy. So using this formula, delta U equals 4 times 10 to the minus 6 into 250, because that's the change in electric potential, which gives us 1.0 times 10 to the minus 3 joules. Now part B. But before part B, we have a given. A proton of a certain mass is released from rest in a uniform electric field of magnitude this, directed along the positive x-axis. The proton undergoes the displacement of 0.6 meters in the direction of E. B is asking us, what is the change in electric potential? One thing you should know, the change could be positive or negative. Either it's going from low potential to high potential or high to low. But how do we know which one is it? Well, naturally things tend to go from positive to negative, right? The electric field is like this. And since it's going from rest and having a displacement without any external forces, because they don't mention any, it's from plus to minus. So the change in electric potential, shouldn't it be negative? Because let's say if it's 100 here and it's 50 here, the change is negative. So that's why delta V has to equal minus ED. If you remember, we said V equals ED, so delta V equals minus ED. So it's minus 7.5 times 10 to the 4 into, what's the distance, 0.6, giving us minus 4.5 times 10 to the power of 4 volts. Part C now. Find the change in potential energy of the proton. Again, delta U equals Q delta V. The proton has, now the proton's charge has to be memorized. This is a constant and you guys should know it. It's 1.6 times 10 to the minus 19 times, you get this answer. And then you should get minus 7.2 times 10 to the power of minus 15 joules. And now let's move on to the last part, D. Let's see what they want us to find. What is the speed of the proton after it has moved 0.6 meters starting from rest? One thing I would like you guys to know, since there are no external forces acting, there is one thing that is conserved, mechanical energy. Now, if you remember, we used to say U1 plus K1 equals U2 plus K2, right? But here we're not talking about gravitational potential energy, we're talking about electric potential energy. So what is the energy we have lost? 7.2. But since we don't need to have it negative, it's 7.2 times 10 to the power of minus 15 is equal to half mv squared, right? The kinetic energy, the mass is 1.67 times 10 to the minus 27. Yeah. And this is v squared, and the v should be v equals 2.94 times 10 to the 6 meters per second. And this is the velocity of the proton. Let's move on to question 4 now. A 3 microcoulomb point charge is located at the origin, and a second point charge of minus 6 microcoulombs is located on the y-axis at the position 0 and 2 meters. A says find the total electric potential due to these charges at point P, whose coordinates are 1.5 and 0 meters. So I'll give you guys a few seconds. You guys can solve parts A and B, and then we'll check. Okay, let's solve it together. First, what we should do is we should find let's call the one at origin Q1, and let's call the one at the this position Q2. So let's find V1 first, which is KQ1 over R1, and since it's let's see, 1.5 meters away from the axis, so it's from the origin, sorry, 3 times 10 to the power of minus 6 over 1.5, 18,000 volts. Let's circle it because it's not the final answer. Now let's find V2 as well. This is again KQ2 over R2, which is K, 9 times 10 to the 9. Now this is minus 6, the sign is important here. Minus 6 over, now what's the distance? We should do Pythagorean theorem here. Let's see, 1.5 squared plus 2 squared. I'm going to let you guys do all the calculating there, and we should get minus 21,600 volts. And this is circled as well because we still haven't found our final answer. We've just found the electric potential of one and the other. Now let's find the final electric potential. Let's call this V net, and this is equal to 18,000 minus 21,600, which gives us minus 3,600 volts. Let's go part B now. What is the work required to bring a minus 3 microcoulomb point charge from infinity to the point P? Now we should remember what's the formula of what is the question? Work required or potential energy. It is K Q1 Q2 over R. One thing we should know, if R is infinity, isn't U 0? So U infinity is 0. This is one thing. Now if you guys think about it, when you're trying to take something from a lower potential energy to a higher, since we know at point P it's definitely going to be higher than 0, then do you need to do work, or is the work external or internal? external, right? Let's say you're taking a bucket of water. It's not going to go up, like if you have a river, it's not going to go up a mountain by itself. It needs to be pushed up the mountain. It's going to fall by itself, but it's not going to go up by itself. So work external here is equal to Q. Now here we have VB minus VA, right? Since we're talking about potentials here, so we have to do Q, which is minus 3 times 10 to the minus 6 into minus 3600, which gives us an answer of 0.0108 joules. So it's going to take a very small amount of energy to bring it from infinity to point B. Let's move on to question 5 now. I'll give you guys a few seconds and you can check, you can solve, and then we'll check together. Let's solve it together. What is the change in potential energy a 16 microcoulomb charge experiences when it is moved between 2 points for which the potential difference is 75 volts? Okay, we should remember that delta U, which is the change in potential energy, is Q delta V. If you know this, is very easy. 16 times 10 to the minus 6 into 75, which gives us 1.2 times 10 to the minus 3 joules. That's it. B now. The gap between the electrodes in a spark plug is 0.08 centimeters. To produce an electric spark in a gasoline-air mixture, an electric field of 4.5 times 10 to the 6 volts per meter must be achieved. When starting the car, what is the minimum voltage that must be applied by the ignition current? This question is very big, but it's actually very simple. You have two electrodes. One is negatively charged, one is positively charged. The direction of the field is this, and it's uniform. Now what is the formula when it's uniform? V equals ED, and we have ED. It's 4.5 times 10 to the 6 into 0.08 times 10 to the minus 2, dividing by 100, and we should get 3600 volts. So this is the minimum voltage that must be applied by the ignition current. And we're done with question 5. Finally guys, let's move on to question 6. What is the speed of a proton of mass 1.67 times 10 to the minus 27 kilograms that is accelerated from rest through a potential difference of 105 volts? So I'll let you solve for a few seconds and we'll check together. Now we should remember conservation of mechanical energy, and we should know the formula for delta U, right? Equals Q delta V. Now now you guys may be thinking, oh, what's Q? Well, for a proton, it's 1.6 times 10 to the power of minus 19. We have delta V 105, which leads to 1.68 times 10 to the power of minus 17 joules. And this is the loss, or it could be the loss or the gain of potential energy. But we're looking for the speed. So we should write delta U equals delta KE. So the kinetic energy loss or gain is equal to the potential energy loss or gain. So then what follows is delta U equals half mv squared. Since it's accelerated from rest, so minus half mv0 squared, v0 is 0, so it cancels out. So now that we have this, it should be 1.6 times 10 to the 68, times 10 to the minus 17 equals half. The mass is 1.67 times 10 to the minus 27. Since the mass is so small, we should expect a very big speed. And the velocity finally is 1.42 times 10 to the power of 5 meters per second. So this is the speed of the proton that is accelerated from rest through a potential difference. Moving on to question 7 now. An electron of mass 9.11 times 10 to the minus 31 kilograms. And one thing to note here, you might need to memorize this. Sometimes they might not give it. So just memorize the mass of an electron. Moving parallel to the x-axis has an initial speed 3 times 10 to the power of 6 meters per second at the origin O. Its speed is reduced to 2.1 times 10 to the 5 at point A. Find the potential difference of VAO of point A relative to origin O. I'll give you guys a few seconds, you can solve. Here I'm just giving a graphical representation of the given 2.1 times 10 to the power of 5, right? And we want potential difference VAO. Now again, conservation of mechanical energy. So we have a certain mechanical energy, let's call this ME1 and ME2. These two are equal, so we can say very easily U0 plus K0 equals UA plus Ka, right? Anything cancelling? No, nothing is the same, so we should continue on. Q times V0 plus half mV0 squared equals Q into VA plus half mVA squared. We have the mass, we have the velocity, we have Q, we have M, V0. All we need to find is VA and V0, right? So when we solve, it's basically the charge of a proton is, electron is minus 1.6 times 10 to the minus 19, V0 plus half the mass. You substitute V0 equals the same charge, you substitute VA, and then you just substitute. I don't have the space here, so I'll just write, you should get VAO to get minus 25.5 volts. So it's going from a higher to a lower potential, right? Moving on, number 8. 3 charges in the figure are at the vertices of an isosceles triangle. Immediately we should know that A, B and AC are equal, and they have said that AB equals AC equals 5 centimeters both sides, and BC is 4. Q1 is plus 4 microcoulombs, Q2 and Q3 both are negative 4. O is the midpoint, so this is 2, 2. A. What is the potential at O due to Q1? So I'm just going to call at O V1 because then it makes it's easy for us. We should know that it's KQ1 over R1. We have K, we have Q1, but we don't have R1, the distance from A to O. How do we find it? Oh, sorry, let me just try to make a straight line. This is 2. Let's draw a line, black or red actually. Perfect. Well, Pythagorean theorem, so it's 9 times 10 to the 9 times 4 times 10 to the minus 6 over the square root 5 squared minus 2 squared, and when we solve all that we should get 7.86 times 10 to the power of minus 5 volts. B. What is the potential at O due to Q2? Okay, Q2. How do you find that? Using the same formula, KQ2 over R2, we have K, 9 times 10 to the 9. This time we have to use the negative, so it's minus 4 times 10 to the minus 6 over. Now what's the distance? It's obvious that it is 2, right? So it is 0.02, and one thing I forgot to mention here, it has to be in meters, so you have to convert accordingly. And you should get minus 1.80 times 10 to the power of 6 volts. Can anyone tell me something special? V2, or the electric potential at O due to Q2, is equal to V3. Why? Because same distance, K is constant and the charges are the same. So this will be very important when we come to part C. Part C now. Total electric potential at O. So what we have to do is you have to do V1 plus V2 plus V3, and using this we can find our answer. So let's call this V total equals V1 plus V2 plus V3, which is simply V1 plus 2V2, which is, let's write this like this, 7.8 times 10 to the 7.86 times 10 to the 5 plus 2 times minus 1.8 times 10 to the 6, and we should get minus 2.81 times 10 to the power of 6 volts. Moving on to the last part now. A point charge with Q0 with 3 microcoulombs. So now we're finally putting a charge here, and this is Q0, is placed at O. Find the electric potential energy at associated with QO. U, we're looking for U, is equal to QV. We have the V, minus 2.81 times 10 to the 6. We have Q, it is 3 microcoulombs times 10 to the minus 6. Since the same cancels, it's minus 2.81 times 3. We should get minus 8.43 joules. Not that big of an energy amount, but it's minus 8.43 joules. Finally, moving on to the last question for the electricity required material for the periodic, question 9a. 2 point charges Q1 7 nanocoulombs and Q2 minus 2 nanocoulombs are separated by 36 centimeters. What is the potential energy of the pair? And find the electric potential at a point midway between the charges. I'll give you guys a few seconds and then we'll solve together. Let's solve it together. They're looking for the potential energy of the pair. The very first equation we learned about electric potential is U equals K Q1 Q2 over R, R being the distance. One thing that is different, you may remember another equation, Coulomb's law, Q1 Q2 over R squared. Here Q1 and Q2 is not absolute value, negative sign matters, and we will consider it. So it's 9 times 10 to the 9 times 7 times 10 to the power minus 9 times minus 2 times 10 to the power minus 9 over, is 36 centimeters, so 0.36, this cancels, and we should get minus 3.50 for 3 significant figures times 10 to the minus 7 joules. One important thing, guys, we should take care of the significant figures in the exam because marks will be taken for the answers because it's computer correctable. Moving on to part B, last part. Find the electric potential, or the V basically, at a point midway between the two charges. I've called this point M because it's the midpoint. It is 18 centimeters from both sides. We should know that. Let's call VOM the electric potential due to the origin charge on M. So it's K Q1 over R1, which is 9 times 10 to the 9 times 7 times 10 to the power minus 9 over 0.18. Cancels, we should get 350 volts. Now let's call this VAM, which is KQ2 over R2, the voltage electric potential at M due to A. M due to A is equal to 9 times 10 to the 9 times minus 2 times 10 to the minus 9 over again 0.18. Cancels, and we should get a negative 100 volts. Finally, concluding, V total equals VOM plus VAM, which is 350 minus 100 to give 250 volts. And this is the end of the electricity portion of the physics periodic. I hope you guys understood, and thank you for watching our video.